So these are the notes for 2.3, and here we're going to be talking about functions and what makes a function a function. A relation is any set of ordered pairs. The x is the domain and the range is the y. But a function is special in that every x value or every domain value has exactly one range value, meaning that if you put in an x, there's only one result that can come from it. So if we look at this, if we look at the x values here on this first function, -3 goes to 9, -2 goes to 4, -1 goes to 1, 0 goes to 0, and 1 goes to 1. Each x value has its own y value. It's okay for the y values to match on different questions, different parts, but you can't have -1 going to two different results. And so because -1 only goes to 1, we're okay. Down in the second example, -4 goes to 1 or -4 goes to 3. The fact that there's a choice there at all means this is not a function because it's not perfectly predictable. We need to be able to guarantee the results of a function. Well, determining whether or not something is a function, there's a couple of different ways. But for instance, when we look at this and we're saying put in an x, what do you get for y? One of the first things we look at is what would it look like if we got y alone. In this problem, y would equal -x squared plus 4. If you put 1 in there, negative of 1 squared is -1 plus 4 is -3. Nothing about that seems strange. It's just pretty standard. I found an answer. When I get y alone here, y squared equals -x squared plus 9. And that doesn't seem unique all that much until I have to get rid of this square. To get rid of a square, you take the square root. And when you take a square root, you always put a plus or minus in front. So y would equal plus or minus square root of -x squared plus 9. So the issue here that we're going to start to have is that if I put a number like, let's just put 0 in. Yeah. If I put 0 in here, 0 squared is 0, plus 9 is 9. So y would equal plus or minus the square root of 9, which is plus or minus 3. But because I have a plus or minus, that means I have two choices. I shouldn't have choices when I'm dealing with a function. So this is a function. This is not a function. And we're going to talk about other ways to tell as well. But whenever we have that plus or minus in front of a square root, or more specifically, if the equation has a y squared, that's a good indication that we might have a problem. Function notation is just a way to write it, to tell everybody this is a function, and be able to do some really simple substitutions. Okay? F being a function of x, x being what we're going to put into the function, produces, and this is the output, 3 times the input plus 1. And we know how to do this math, but the notation is kind of something that sometimes gets difficult to work with, for people to get comfortable with. But they are used all the time, especially when we're talking about Excel spreadsheets and things like that. When we program things, we typically use function notation so that the computer can understand input and output. And so in the world we live in where technology is so important, understanding how to read function notation is important. For instance, this is function f right here, but we're asked to put -5 as the input. Do you see how -5 has gone where x is? That means we're going to put -5 wherever x was. And then we'll simplify. -5 squared is 25. -2 times -5 is a positive 10, and the plus 7 was always there. This becomes 35 plus 7. That should be 42. So f of -5 is 42. Sometimes it gets a little weird because we don't want to just substitute numbers. Sometimes we want to substitute an equation inside of an equation. That's what we're doing right here. Everywhere there's an x, I'm going to put x plus 4, meaning I'd have x plus 4 squared minus 2 times x plus 4 plus 7. Can you see the same notation or same structure in the problem? It's something squared minus 2 times that thing plus 7. Well, I've got to square this by foiling. Gives me x squared plus 8x plus 16. And then we FOIL minus 2x minus 8 plus 7. And so if we look, we get x squared plus 6x excuse me, and that should be plus 15 when I'm done. That new equation is the function f with x plus 4 substituted inside of it. So we're doing equations inside equations, but this function notation allows us to do that really easily. Here we're going to see what happens if we just make x negative. What happens to the equation? Well, we would get negative x squared minus 2 times negative x plus 7. Well, negative times negative is still positive x squared, but here we're going to get a positive 2x plus 7. Now if you look at the original function and this function, they're not very different. In fact, the only difference is this 2x became positive instead of negative. But we're allowed to substitute inside. In this function notation, do you realize how much it would take to write? If substitute negative 5 into the function x squared minus 2x plus 7 and simplify. That's a lot of words where this is all I have to do. Okay, so it's about simplification. We have what's called the difference quotient, and the difference quotient is an extremely important concept that drives pre-calculus and calculus. It is something we still study here. It's the equivalent of finding the slope of a function. The difference quotient allows us to do that for any amount, and that the smaller the h, the more accurate our function slope will be. But think of it a little like finding the slope. But this is a process we're gonna go through and do. Find the difference quotient. So right here, okay, f of x plus h. Okay, this right here. That means I'm going to take this equation, the f of x, but instead of putting in x, I'm going to put x plus h. That makes it 6. Instead of putting x, I put x plus h minus f of x is the original problem, 6x over h. Now if I distribute, okay, I'm going to get 6x plus 6h minus 6x all over h. There's negative 6x and 6x cancel, and 6h over h is just 6. Now I told you it was the slope, and since this is a straight line, the slope was 6, and there we can see it. With other equations, it can get more complicated or less complicated. Let's try this again. Right here is where I'm going to do all my substituting. So 2 times x plus h plus 1. There's the original problem with x plus h, where x was. Minus, and this gets a little hairy, so I'm going to parentheses 2x plus 1. I need to make sure I distribute the negative. So I always put that in parentheses. But remember, this is just the original equation. That's what f of x is, the original problem. And that's all over h. So I'm going to distribute. I'll get 2x plus 2h. It says plus 1. And when I distribute here, I get minus 2x minus 1. And that's all over h. The 2x's cancel, the 1 and the negative 1 cancel. I'm left with 2h over h, which is 2. If it's a straight line, you're literally finding the slope, which is a beautiful thing. But the substitution process is important because sometimes it's not just a straight line. So anyway, let's look at what's called a piecewise function. The reason it's called a piecewise function is because it's broken into pieces by its domain. Now, a piecewise function we have to read from right to left. So if this is our equation and we're asked, what is f of negative 7? First, I have to figure out where negative 7 fits on my scale. Is negative 7 less than 0, between 0 and 3, or greater than 3? Well, negative 7 is less than 0. So I will use this equation. So negative 7 squared is 49, and that'll be my answer. Look down here, when it's 2.5, well, 2.5 is between 0 and 3. So I will use this equation. You might ask, well, where do I put the x? Where do I put the 2.5? Because there's no variable, the answer is just 2. If I had gotten something greater than 3, say for instance 5, because it's greater than 3, I would have 4 minus 5 and get negative 1. So I'm just going to read from right to left so I know which formula to use. And once I know which formula to use, I just plug it right in. The last thing we need to really make sure that is clear is how do we find the domain? Any value that causes division by 0, so no denominators of 0, or results in an imaginary number by taking the square root or fourth root of a negative, is not allowed in the domain of a function. So, we're going to find the domain for all of these. The first question, is there a square root in function a? No. Is there a denominator with x in it? No. So, the domain is all real numbers. This is the symbol for all real numbers. Here, we have a problem. I'm not allowed to let this become negative. So, for practice purposes, for practical purposes, we're going to say let it equal 0. If it equals 0, x would be negative 2. And the square root of 0 is 0. That's okay. But if I go to negative 3, negative 3 plus 2 is negative 1, and I've got a negative inside the square root. So, negative 2 is the last good value, meaning that the domain, okay, would be x has to be greater than or equal to negative 2. And this last one, the thing I have to avoid is letting the denominator be 0. That's not actually allowed. Well, the only value that wouldn't work is the 5, because 5 minus 5 is 0. So we would say the domain is x does not equal 5. Now there are different ways to write these domains. Remember, we've done interval notation in the past. So this all real numbers would be from negative infinity to positive infinity. The domain being greater than or equal to negative 2 would mean, bracket at negative 2, comma, go to infinity in parentheses. And this last one, we would have negative infinity all the way to 5, but don't include it, so use a parentheses, combined with starting at 5 and go all the way to infinity. So this setup right here, it's because there's no bracket on 5, it's telling me that 5 is not allowed to be used. So these are different ways to look at the domain and the way that it's written. Good luck, and we'll see you in class.